Hi all, in this video we have two masses. One of the masses has a mass 2m. It's connected by an inextensible string, so that means this string does not stretch or compress. It's more or less a string that's like a rod, so it's not going to move at all. Or it will move, it just won't stretch or flex. Connected to another mass m. So there's a tension T in between here, which is an unknown. Known so far are 2m and m, and there is a force F being applied to them, which is a known. So this is a frictional surface, and we're given that these are accelerating. So our two options for forces due to friction are the static friction and kinetic friction. Since these are moving, and not only are they moving, but they're accelerating, we're going to be using the kinetic friction. So there's going to be a mu k acting where both of these are hitting the ground. So the first part is draw two force diagrams. So for the mass of 2m, we're going to call acceleration to the right positive. I'm going to treat it as a little point mass. We will have a tension to the right because the tension is what is actually going to be pulling this mass. And there's going to be a frictional force to the left, which we'll call F sub 2. The reason why there is a frictional force to the left is this mass will be moving to the right and friction opposes the direction of motion. We will have weight, which will just be m2, or sorry, we know that m2 is 2m. So this is just 2m times g, and that there's a normal force, n2. That's for this mass on the left. The other mass, we're going to call acceleration to the right positive. I'm calling these accelerations both to the right being positive just so that things are convenient. This will make our constraint later much easier. So we'll treat this mass as a point mass. So it's going to have a weight, which is mg. It's going to have a force to the right, which is F. And there will be a force to the left, which is tension. And there's also going to be a force to the left, which is what we'll call F1. So F1 will be the frictional force opposing the motion of this mass as it moves to the right. Finally, there is a normal force N. So that's A. B is using a coordinate system such that the x direction is positive, apply Newton's second law, and write down two equations for each mass. So now what we do is we use our force diagrams. We'll do the x first. So we'll have 2m a, let's see, call this a1, call this a2x equals to t minus f, and then 2m a2y is equal to n2 minus mg. And over here we'll have ma1x is equal to f minus t minus f1, and then ma1y is equal to this should be an n1 minus mg. Okay, so now part C is apply the constraint that these masses aren't accelerating in the y direction, in the vertical direction, so they're not going into the horizontal plane at all. So what simplifies this to is just that we now have 0 equals to n2 minus mg. Oh, sorry, should have been a 2 here. So this is just 0 Likewise, this is 0, so we'll get 0 equals to n1 minus mg. So that's C. And then D is how is this acceleration and the extraction related to that acceleration? They're equal to each other. We'll just call that A. So that's D. So now we want to write down these equations using the frictional forces, the normal forces, acceleration in terms of given quantities only. So what we want to do is we want to solve for either the acceleration A in terms of given quantities, or we want to solve for the tension T. So we could do this a couple different ways. The way that I will suggest doing it, the same way as the notes. So what we'll do is we'll just add the two horizontal equations of motion together and then solve for the acceleration. So now if we just add ma, we'll call this A, equal to, so that's F2, F1, F minus T minus F1. So we add these together, we'll get 3ma is equal to F, and the tensions will cancel, so we'll get minus F2 minus F1. And what we know is that there is no acceleration in the vertical directions, so the normal force will be equal to the weight of each one. So we can rewrite this as 3ma is equal to F minus mu k 2mg minus mu k mg. And then we can just add these together, so we'll get 3ma is equal to F minus 3 mu k mg. We can now solve for A, so dividing over by 3m, we'll get A is equal to F over 3m minus 3 mu k mg all over 3m. The 3's will cancel here as well as the m's, so we'll get A is equal to F over 3m minus mu kg. So this is nice because we need to get something as units of acceleration, gravity as units of acceleration. Mu k is just a number between 0 and 1, and then force divided by mass is equal to acceleration. So that's great. Now the last thing we need to do is also figure out the tension in terms of given quantities. So one thing that we can do is just use this right here and solve for the tension, since we know the acceleration now. So rewriting that, we'll just get 2ma is equal to T minus F2. So that's 2m times A, which we found was 3F over 3m minus mu kg is equal to the tension minus 2 mu k mg. We'll get this over to this side. So now we'll multiply, no, let's do this one step at a time. F over 3m minus mu kg, just rewriting that, plus 2 mu k mg is equal to the tension. And so we have tension in terms of given stuff. Now we just need to simplify this. So we'll multiply this into here, into here. So we'll get F 2m over 2m times F over 3m minus 2m mu kg plus 2 mu k mg equals to tension. These two cancel each other out. This is m over m, so now we get 2/3 F is equal to the tension. And that was the last bit. Thank you very much.